Now in part 3 of the hydrological cycle, we're going to go underground. We're going to talk about the activity of water beneath the Earth's surface. And the first thing we'll discuss is what's known as Karst Topography. The characteristics of Karst Topography, the region that is karstified, include high rainfall and abundant vegetation, limestone bedrock, or more rarely dolostone bedrock, with joints. These joints are fractures that are introduced into the rocks under varying tectonic regimes. So compressional, tensional, these types of stresses will put these joint sets in the rocks, and that's the conduit the water is going to tend to follow. There's generally a significant hydraulic gradient involved as well. Impetus, a gravitational directive for water to move through these subterranean features. So here they are, all characterized in cartoon form. We'll start out with surface features, sinkholes. These are depressions. If there's simply a depression, it's often called a doe-line sinkhole, but in general they're called sinkholes. And this is a collapse structure. So that implies there's some opening beneath the sinkhole. And it's the collapse of the cave roof that forms the sinkhole ultimately, kind of like a mini caldera. So in this case, instead of emptying a magma chamber and the walls falling in on you, you remove the limestone underneath and the walls fall in on you. Associated with these sinkholes are going to be soil that falls in there, rocks fall in there. When I was working in Missouri as a geologist, I was looking at a sinkhole in some Mississippian rock, and it contained seeds from plants that were of some age, probably Mississippian in age. So we'll say roughly 300 million years old. So it's kind of cool to find that stuff, that debris that was formerly on the surface of the earth falling into that cave and then getting buried. If we go a little further down into the rock, we're going to eventually reach the water table. And that water table is going to vary throughout the year and throughout centuries, rising and falling in response to changing precipitation above. This groundwater may be supplied by a river, or the river may represent the groundwater surface, the water table surface. So ultimately, a series of caves is going to be generated in this limestone terrain, and it's going to be generated by a combination of water with vegetation. The role the vegetation plays is that as it dies, it is broken down by bacteria predominantly. And those microbes that break down that organic matter produce acids. They also produce CO2. And we now know that CO2 mixed with water is carbonic acid. So that carbonic acid drains down through these limestones. And for those of you taking geology lab, you'll know that if you add acid to a carbonate rock, it fizzes. That fizz is CO2. So that's happening at a lower rate here with less acidic water, but nonetheless the same thing's happening. Ultimately, this rock is going to dissolve as this acidic groundwater pours through. When it reaches the opening in the cave, though, the partial pressure, the amount of CO2 in the cave atmosphere, is going to be lower than the amount of CO2 in the rock itself, in the groundwater that's flowing through the rock. So when water hits this opening here, this is very important, this is critical, this is a must know, that water reaches the opening of the cave here, it's going to degas, it's going to give off CO2, just like opening a can of Coca-Cola that's been shaken up, or a fine craft India Pale Ale. When you open it up, that CO2 is more concentrated in the can than outside of the can, so it is given off. And it's given off vigorously in the case of those two examples. When that happens now, the amount of acidity is reduced in the water that's within these rocks. And because the acidity is reduced, just the opposite happens of adding acid. We're going to get precipitation of carbonate. It's going to precipitate as the water droplet is moving down from the roof of the cave in the form of a stalactite. And when the drip hits the floor of the cave, it can form a stalagmite. So stalactites come down, stalagmites go up. And eventually they can join, forming a column. Now, these cave environments are nearly 100% humidity, nearly saturated with water vapor. And importantly, they are at the mean annual temperature of the region. So we can use a cave for climate information. If we take some of this calcium carbonate from the cave and we dice it up and analyze it for its oxygen isotope values and its carbon isotope values, we can use those values to determine how temperature and precipitation have changed in the past. Occasionally, these caves may express an opening at the surface that you can easily find and climb into. You may have seen in the news just recently, a number of caves have been explored. A huge number of caves have been explored in Israel by rappelling down a cliff face into the cave. And in one of these caves, they found some new Dead Sea Scroll material, as well as a 10,500-year-old perfectly preserved giant basket from the Stone Age. So ancient writing on ancient paper that was stored in these caves thousands of years ago. In the case of Israel, the caves are dry and good for preserving things. In the case of many other areas, the caves are wet and not so good for preserving things like paper. Now, what the caves look like inside, here we have some stalactites hanging down, some stalagmites growing up, meeting to form a column. We can have things that look like curtains of rock here, which can be called curtains, and little straw-like features that are hollow that we call soda straws, and a whole bunch of other terminology for the kinds of things you'd see in caves. I edited an article a few years ago for a kids magazine called Yes, the Science Magazine for Kids, something like that. We talked about all the different kinds of features that you'd see in a cave. Now, some dramatic examples of sinkholes. These are found very commonly in Florida because Florida is essentially limestone, almost the whole state, and therefore the whole state is susceptible to a lot of problems, as you may know if you watch the news. Florida man. Florida also has a sinkhole issue. There is a documentary on National Geographic called Sinkhole, Swallowed Alive that was narrated by a former graduate student of mine, Matt Kirby. So you can probably find that online. Sinkholes Swallowed Alive, something like that. Pretty good. Now this is something that's so crazy and so spectacular that, like everyone else, maybe not like everyone else, but like me, I thought that's fake. So I Googled it and it's not fake. This is a real sinkhole in Guatemala that opened up after a tropical storm passed through. So the tropical storm flushed the karst system below the city and washed away all the debris in the caves. Well, washed more debris into the caves, but also washed debris away. And in doing so, it undermined the material lying above. That's often volcanic in this part of the world. And as this pyroclastic material was positioned over an open void in the earth, it fell straight down. I don't know how deep this is, but it looks pretty deep. Apparently it swallowed one building, which I'm guessing was here, as well as the intersection. So really crazy, spectacular things do happen, even to this day in karst. This brings us to water quality. If we have this water flushing through the ground and we obtain much of our drinking water, irrigation water, industrial water from the ground, we need to think about what's in that water. What's the history of that water? Is there anything we should be concerned about? And yes, there are many things to be concerned about. Lead pollution is something that we introduced directly to our water supply by using lead pipes. In a more indirect way, we have a long history of burning things that have lead in them. This can be anything from industrial processes to the use of leaded gasoline for decades. And this was portrayed in one of the stories I listed for you about Claire Patterson determining the age of the Earth. Lead pollution was a problem in determining the age of the Earth because it contaminated everything. It messed up all of Patterson's numbers, and it's because we were burning gasoline with this toxic lead compound in it. So that lead went all around the world. Whenever it rained or snowed anywhere, it collected some of that atmospheric lead and threw it into water supplies everywhere. So a friend of mine did a study on Lake Erie. They took a sediment core out of Lake Erie and they diced it up. And you can see in the lead isotopes in the sediment when countries switched from one lead source to another. When the Roman Empire rose, they had lead sources that were obviously convenient to the Roman Empire. Subsequently, lead sources shifted elsewhere, including to the United States. The viburnum trend in the central U.S. and the St. Francis Mountains, eastern Missouri, those were two prime lead areas called lead belts. And they were used to make lead batteries in our cars and lead pollution in our gasoline, things of that nature. Radioactive waste, we need to get rid of radioactive materials that we generate, that we concentrate. One way is putting it in the ground. You don't see it anymore, problem solved. Unless you want something out of that ground, like drinking water. It becomes a very big problem. One of the last jobs I had as a geologist in the state of Missouri was to look at a Superfund site. These are major toxic waste problems usually that are given hundreds of millions of dollars to fix. In this case, it was St. Charles, Missouri. It used to be the capital of the state of Missouri. Now it's been moved to Jefferson City. When St. Charles was a big deal, there was a couple plants there, chemical plants, making DNT and TNT. In World War I, they dumped the waste in these pits out back. Eventually, those pits percolate and leach into the surrounding sediment and then right into the caves that underlie St. Charles, Missouri. In World War II, they turned the plant into a uranium refinery. So they were refining yellow cake. When I visited back when I was in my early 20s, we were told to stay on the plastic at all times. If we stepped off the plastic, they would confiscate our footwear. People were working in these plants for decades, and we weren't allowed to step off the plastic. So keep that in mind. On top of that, on top of the radioactive waste and the industrial explosive waste, the plant was entirely encased in asbestos. So when they asked me what could be done, I basically said nothing. You're on your own, really. Once radioactive material gets into the karst, into the groundwater, it's there forever as far as we're concerned. Microorganisms in groundwater can be a problem if these are toxic to us. If these are microorganisms that kill us, for instance, that's a problem. Other chemical contaminants, we talked about lead from burning gasoline. We talked about radioactive waste. We're pumping things like that into the ground to get rid of it, to hide it. We also have contamination from other sources. When a coal power plant produces electricity, like the electricity that's used here in Saskatoon, that coal generates a lot of pollution. That pollution includes mercury and arsenic coming out of the stacks, blowing downwind, and being deposited by precipitation into those local water reservoirs. That's an ongoing issue. Here we have some examples of bad things people do. We have a waste lagoon. This would be similar to those raffinite pits in St. Charles, Missouri. We dump our waste into the lagoon, and you hope it stays there. It, of course, doesn't. Even if you line it with rubber or plastic, which some people do, it eventually degrades, and whatever is in that plastic or rubber bowl leaks into the ground. And then it just moves around for the rest of human history. Landfills, which contain anything and everything you could imagine, are slowly leaking into groundwater all over the world. If that impinges upon a river, the river will take some of that waste to someone else. Fertilizers, irrigation, and pesticide application, these are the agricultural pollutants. These are very, very significant as well. Now, fertilizer might seem like an innocent thing, but it fertilizes everything. Once it's in the groundwater, it fertilizes the groundwater. Microbes love that stuff. When it enters a river, gets pumped into the ocean or a lake, the aquatic organisms love that fertilizer, and they have an algal explosion. Lake Erie will turn bright, slimy green, and that looks neat from space, but what it is so much organic matter being produced so quickly because of this fertilization that when that organic matter dies and breaks down, it sucks all the oxygen out of the water, and that kills anything in the water that needs oxygen, like fish and clams and zooplankton, etc. So by adding too much fertilizer to a field, you can kill off a lake. Who'd thought of that? Who would have ever thought of that? Pesticides, we're putting things that kill organisms into our groundwater and then drinking it. Use your imagination. Septic tanks located everywhere. There's no connection to a civic sewage system. These eventually leak and break down and spread those contaminants. If it's natural waste, it's really not that much of a problem. It's all the other stuff that people throw into their sinks and toilets that they flush into their septic tank that enters the groundwater. That's a big problem. One of the biggest problems is the burial of gasoline and industrial chemical storage tanks. These are put in the ground to store material like gas, diesel, and then the gas station goes out of business 20 years later and they sell the property. That's it. That tank is still in the ground with diesel and gas still in it. It might not be a lot. It might only be 100 or 500 gallons or so. But that 500 gallons of diesel fuel dumped into the groundwater that you're going to drink at some point makes the water taste like diesel fuel. And some people don't like that nearly as much as others. So these are just a couple examples of the kinds of things that people are doing to ruin the future for other people. There's a huge industry of people that go around and remove these tanks, and they're known as tank yankers. It's not entirely a positive thing to be called. Arsenic. Who doesn't think about arsenic when they drink water? This is going to be a problem that is related to geology and related to the power supply. So if we have geological formations that contain significant arsenic that's mobilized, we end up drinking it. It goes into our drinking water, it goes into our irrigation water, our swimming water, etc. Arsenic can also come from the burning of fossil fuels like oil, gas, diesel, coal. All these things contain arsenic, and by burning these things to generate energy, we release that arsenic to the world. We need to improve the quality of the water if it's possible. This is known as reversing contamination. Now, it's easiest to reverse contamination if the recharge rate is fast. I don't know what is going on outside right now, but it's getting louder and louder. Usually, this reversal of contamination is very costly and very slow, which means nobody does it. Decontamination after pumping is possible if it's done correctly. Again, that's usually expensive, usually not done. And then there are in-ground water treatments. These are relatively rare, relatively ineffective, but in some instances they can generate an improvement. So the outlook is grim. The inside joke that people tell about pollution, these are mine waste people and general pollution people, is the solution to pollution is dilution. If you wait long enough, the problem goes away. It might take 5,000 years, 20 million years, 100 million years. The problem will go away. Do we have time to wait for it? That's the question. Potable water, drinkable water, is generally water that has less than 150 parts per million dissolved material, non-water ions. Distilled water generally has less than 1 part per million of dissolved solids. And some elements like arsenic, which are particularly dangerous to us, have a very low limit, a safe limit. 0.05 parts per million. Very, very little arsenic will begin to cause problems for you if you're consuming it regularly. Okay, now going all the way down to the bottom of the hydrologic cycle. We're in the deep crust. There's water present in the deep crust that comes from precipitation, meteoric precipitation ultimately. It works its way down, 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 hundreds, thousands of feet to where it reaches all the other water that's collected at that depth. We can have magmatic water that's derived from igneous sources and hydrothermal water, which is ultimately meteoric precipitation that percolates into a shallow depth, gets heated, and then rises back up, as we've seen the eruption of Old Faithful and Geysers in Iceland. So what this looks like here is near the surface, we have considerable porosity and therefore lots of space for water. As these grains get compressed by overburden, overlying pressure, the porosity decreases. Ultimately, we reach a depth where porosity is low and we no longer have pure, nearly pure fresh water. We have a mixture of fresh water, crustal water, and old seawater. So this is non-potable. You can't drink this stuff. And the basement rock is going to have very low porosity because The minerals are crushed together by extreme pressure, and the conductivity is going to be low as well. The ability of water to move from one pocket to another is going to be severely limited. So although there, in terms of the bulk of the earth, is a lot of water down here, it's not obtainable. And if we did obtain it, it wouldn't be particularly useful to us. It would be briny, radioactive, and infested with dangerous compounds and elements. Now, geysers are a bit of an oddity. Geysers result when meteoric water infiltrates the soil, works its way down through permeable rock, where eventually it gets heated. And if it's heated sufficiently, it will rise to form a hot spring. This could be anywhere from warm to boiling hot. If the plumbing is more complicated, we can have pockets where steam can form. Eventually this steam is going to build up sufficient pressure such that when a little bit of water bubbles off, that releases enough pressure for this to flash. And when this flashes, it reduces the pressure further, blasts out. Now all these other chambers that are also waiting to go, waiting to erupt essentially, flash to steam, go off, and we get the big blast out of the geyser. Just recently, some people lowered cameras into a number of geysers, and what they found was what they hoped to find. You could drop a probe down a number of meters, say 7, 10 meters, and eventually there's a constriction. So essentially the pipe gets constricted, and that allows for the pressure to build up below, and it allows for that water to stay relatively cool and stable above. Again, once the pressure builds, we push some of this overlying water out. We reduce the hydrostatic head, the pressure on the lower water, and that allows the geyser to blast into the atmosphere. Now, if the geyser is forming in or above carbonate rock, it will form features like this. This is Mammoth Hot Spring in northwestern Yellowstone Park near the Bozeman entrance. These are terraces made up of a mixture generally of aragonite and calcite. So we take carbonate rock, we dissolve it in hot water, hot acidic water, and when it reaches the surface, degasses, cools off, and it leaves these carbonate deposits. If the geyser forms over silicate rock, it doesn't form these terraces. It forms a mound usually, like Old Faithful. So Old Faithful is representative of hot water blasting through silicious rock. It forms a silicious center or an opaline crusty kind of stuff, whereas hot water blasting through carbonate rock forms aragonite and calcite terraces. These can form at low temperatures naturally in some lakes like the famous park in Croatia, Plitvička, something like that. It's very cool. One of the cool things now is that deep in the crust, we find microorganisms. We find living things everywhere we look, including at the very bottom of the hydrologic cycle. These are colonies of microbes that have been there likely for millions to hundreds of millions of years. Again, they're found everywhere. There are worms found in very hot rock in South Africa, thousands of feet below the surface. They've been there for a very long time. They're going to be there after we're gone. And they live not by relying on the sun for energy, but by relying on chemical reactions. Just recently, somebody popped open some rocks from the Atlantic, I believe. And these rocks were basically sealed up 100 million years ago, and they popped some microbes out and brought them back to life. So that's cool and potentially a serious problem. If these microbes are after us, they've had no competition for a long time.